Solid Edge expands its structural and flow simulation capabilities. Starting with structural simulation, in addition to static studies for stress strain, buckling, vibration, and steady-state heat transfer, users now have the ability to study the impacts of heat moving through parts with relation to time, also known as transient heat transfer. This allows designers to see temperature changes over time in order to assess things like heating and cooling performance. In this example, we need to ensure that the heat generated from the motor doesn't overheat the printed circuit board, or PCB, located directly beneath it. A steady-state heat transfer has already been defined here, which takes into account the heat being generated by the PCB and the motor. Using the probe tool, we can query the temperature at different points on the board. Here, the new face probe option allows us to easily find the hottest regions. What we're seeing here is the final steady-state result of heating parts until they have reached full capacity. However, for this assembly, the motor only works for a couple of minutes at a time. As such, to get a more realistic view of the heat on the PCB, we'll use transient heat transfer to accommodate for these working times. This is as easy as copying and pasting the existing study, changing the study type, and defining the working intervals. Then the study can be solved. Viewing the results, we can immediately see the difference in heat distribution of the assembly. As it's only working for 2 minutes, the motor doesn't have time to heat to full capacity, effectively having a negligible effect on the overall temperature of the PCB. The probe tool shows that the maximum temperature is 15 degrees cooler than the previous study. Additionally, selecting any nodes we'd like, Solid Edge provides a graph to easily visualize changes in temperature over time. Solid Edge's transient heat transfer capability gives more precision to the user, allowing for essential visibility into heat distribution of components critical to validating your designs. Turning our attention to flow simulation with Flow EFD, the EDA bridge allows the import of PCB designs for fast analysis. Again, focusing on the PCB, the electronics design for this has been completed in the Solid Edge PCB application. The PCB OBD++ information can be opened via the EDA bridge directly within the Solid Edge assembly environment, where several formats are supported. This automatically generates the board along with the components and copper traces. The thermal properties can quickly be imported in order to apply the thermal data to each individual component. The printed circuit board is transferred to Flow EFD, where the simplified assembly is generated. All material properties, heat sources, and radiative definitions are automatically generated in the Flow EFD project. Loading the simulation results clearly shows the temperature distributions on the board and components. Focusing on the complete design, we can see the effects on the airflow in that part of the assembly. Other new enhancements include the ability to analyze the behavior of fluids moving, sloshing, or pouring using free surface technology, as can be seen here when this trailer comes to an abrupt stop. Compare this behavior to a design that contains baffling in the tank to try and eliminate the excessive sloshing. Viewing the results of the two designs side by side illustrates the benefits of the baffled design. To learn more about Solid Edge, visit solidedge.siemens.com.